Hey guys, so here we are, day one. We're starting in. We're just gonna hit the ground running. We've got a lot of ground to cover, and we've got 45 days to do it. So we're starting with lab number one, topographic maps. It's kind of late tonight while I'm filming this, which is why, as you can see, I'm in the mud room at my house. The rest of the house is all quiet. Everybody's asleep. The visions of sugar plums dancing in their heads, or perhaps visions of Zoom meetings dancing in their heads. I'm not sure. I got 3 kids here who are also doing the whole remote school thing. So, yeah, we got Zoom meetings every which way you can find. Anyhow, this video is going to hopefully get you guys going on lab number one. We're going to have about a week to work on it, and you're going to be working on this during your asynchronous time. So this is going to be, you put in some time in the afternoons. You should have plenty of time to get this done. None of these labs are tremendously challenging, but we don't want to put it off. We want to stay true to our schedule and keep working on it. So yeah, anyways, I apologize for the somewhat rustic background, but hey man, science is science. Doesn't matter whether you're in a fancy lecture hall at Harvard or some random dude's tool room. Anyways, lab number one, topographic maps. Hey, I hope to up my game here a little bit with some, whiteboards and things like that too, but we're going super low tech tonight. Topographic maps. And, it's called the Topographic Map Lab, but really it's not even about topographic maps. So here's how we're going to start. You guys have all, I hope, played battleships before, right? Plug your little plastic boats in on the grid. Your opponent plugs their little plastic boats in on the grid. You got a 10 by 10 grid, and then you take turns guessing. Say, oh, I think you've got a boat in E4, and they go to E, followed over to 4. Then they say either it's a hit or a miss, right? It's great times when you're like 7. A big part of this lab is locating things, and locating things is really, on Earth, is really no different than playing battleships. Only instead of this 10 by 10 grid, we're going to get a little more complicated. So let's imagine, maybe, let's say that you've exhausted the game of battleships as an 8-year-old. You're like, man, this 10 by 10 grid is boring. I need a more complicated, bigger game of battleships. What if instead of the 10 by 10 grid, we still go from A to J, but instead of just 1 through 10, what if we got 1 through 10, but if we go in the other direction, we could go all the way down to negative 10. So now we've got like a 10 by 20 grid. You play that version of battleships when you're 8 and you get sick of that, and you're like, I still need a more complicated game. So now we move up to 9-year-old battleships. Now you've got negative 10, you've got positive 10, you've got A to J, but what if you got like negative A to negative J up here? So you can see what we're doing. We've got a grid. This doesn't look any different than what you've seen in algebra, except that we've got some letters on there. Well, the letters are going to go away. Anyways, because this is all a thought experiment. We're not playing battleships. We're looking at topographic maps. And instead of 1 through 10 and A through J, like we have in battleships, we've got latitude lines, we've got longitude lines. And latitude and longitude are a system It's a system, a grid, just like in the game of battleships, to pick an exact point on the surface of the Earth. This is going to be an important skill for us. In geology, we use a lot of maps. Maps are important to us. In geology, we need to be able to say exactly where something is. That's an important thing as well. And latitude and longitude are the system by which we do that. Pretty simple. Oh, by the way, on these videos, when I make videos, I'll be making a lot of videos for you guys. I like doing things in videos because that way, if you already know the stuff, you can play it at like 1.5 speed. Or if you're like, I need to copy down every word of that, you can pause the video and copy down every word of that. So anyways, I'm going to flash these diagrams and stuff up on the screen. If you need more time to copy them down or whatever, just hit pause and copy them down. This one's pretty simple, right? Latitude, side to side, longitude, up and down, and they are measured in degrees. That's an important thing. Degrees. Why degrees? Well, what's the shape of the Earth? If you're one of those flat earther types, I suggest you go drop the class because it is not flat. It is in fact spherical. Not precisely spherical, but close enough to a sphere for our purposes today. And as you know, spheres are just three-dimensional circles, and as you also know, having passed geometry with flying colors, there are 360 degrees in a circle. So if we're measuring around a circle, it would make sense that we would measure in degrees. And lo and behold, indeed, latitude and longitude are both measured in degrees. You with me so far? Good. I'm about to make it a little more complicated. Maybe you already know all this. That's great if you do. If you don't, this is where it's time to like say, whoa, hold up. Let's start with latitude. Latitude, the lines, so latitude and longitude are these imaginary lines. They're not actually on the ground. You couldn't go find where the latitude and longitude are drawn on the ground. They're imaginary lines. And the lines for latitude run from east to west. They run side to side. Mr. Finn always used to say latitude, fatitude, because it's the fat part of the globe. But here's where it gets tricky. The lines run east to west, but we label them as north or south. Wait, what? Why? Here's why. 0 degrees latitude is the equator. It is, you guys should know what the equator is. 0 degrees. It's around the fattest part of the globe. And so, as we move either north or south from the equator, we cross latitude lines. We cross latitude lines. And so we say that that latitude line is however many degrees north of the equator. Let's see. Or if we got all the way up to the North Pole, visit Rudolph the Red-Nosed Reindeer, we would say we were at 90 degrees north latitude. 90 degrees north. Latitude lines can never go, never going to be a number greater than 90. Why is that? Well, you get up to the North Pole. If you keep going, you're going to start going back towards the equator. So you're going to start going back down in latitude lines if you go over the top and back down the other side of the planet. Same goes for Antarctica with the penguins down there. 90 degrees south is our South Pole. So latitude lines run east to west and are measured or labeled rather as north to south. Here's my next pink page that I've prepared for you, which looks fairly similar to the last one, only it's exactly the opposite, right? We're talking longitude now. Longitude lines, go from north to south. Those lines run north to south, but they are labeled as east or west. Now longitude are a little bit weirder. Latitude behave themselves pretty well. Zero is at the fat part of the globe, right in the middle. 90 degrees at the poles, right? 0 to 90, north or south. But longitude are a little bit stranger. Oh, one other point about latitude lines. They're always the same distance from one another. 1 degree latitude is always the same amount of the same distance. It's the same. Technically, you're following the arc of the outside of the circle of the globe. Anyways, latitude lines are always the same distance from one another. Longitude lines are not, however, because since they run north to south up by the pole, they're really close together, and out at the equator, they're farther apart. Anyways, they run north to south, and they're labeled as east or west. So where's 0? The equator is really easy for latitude lines, but longitude lines, you got to pick somewhere for it to be 0, right? Well, 0's in Greenwich, England. Why Greenwich? Presumably, I think that's where Oxford University is, and I guess the smarty pants who came up with this must have worked there, I would guess, worked at Oxford, and so he decided that they were just the center of the universe, or at least the center of the global coordinate system. And so they said, yeah, here's as good a place as any for 0, and thus it was. And so we can go either east from Greenwich, England, or we can go west from Greenwich, England. And as we move away from 0, we count upwards until we get all the way around the globe to exactly opposite Greenwich, England, 180 degrees. That's called the International Date Line. It's basically out in the middle of the Pacific Ocean, and very few people pay any attention to it. But it's important if you want to, suppose, get into international trading, stocks and whatnot, and it's probably also important if you are doing a topographic maps lab in your Geology 101 class. All right, so what do we have so far? Latitude, side to side. The lines go east and west. The label is north or south. Longitude, go up and down. The lines go north and south. The label is east or west. Where's 0? Greenwich, England. All right. There's a nice little summary there, but this part at the bottom, degrees are actually pretty big. The planet's pretty big. And so the distance between 1 degree of latitude or longitude is actually quite a lot, which makes it rather useless if we're trying to pinpoint a specific location. So we need to divide our degrees into smaller units. Don't ask me why, I couldn't explain it to you. But 1 degree is divided into 60 minutes, and 60 minutes is divided into 60 seconds. So if you were walking west from Greenwich, England, you would start at 0 degrees longitude, right? Longitude, north, south. And we're going to walk west. So we're going to cross longitude lines as we move to the west. So we're going to walk directly west from Greenwich, England. We're going to start at 0 degrees, and we're going to walk. And then after a little bit, we'll cross 0 degrees, 0 minutes, 1 second. And we'll keep on walking. And then we'll cross 0 degrees, 0 minutes, and 2 seconds. And if we walk and walk and walk and walk and walk, eventually we cross 0 degrees, 0 minutes, 59 seconds, and then we get to 0 degrees, 1 minute, 0 seconds. And we just keep adding up until eventually we get to 0 degrees, 59 minutes, 59 seconds, and then finally we get to 1 degree west. And so on and so forth all the way around the globe until you get to the International Date Line. couple of notes about this. Sometimes you will see latitude and longitude expressed in decimal format instead of degrees and minutes and seconds. It'll be decimal degrees. This is becoming more and more common as GPS becomes more important. Also, sometimes rather than seeing western longitudes indicated as positive numbers and labeled west, sometimes you'll just see them listed as negative numbers. So, for example, Mattawa, home sweet home, is at 46 degrees 36 minutes and 39 seconds north and 119 degrees 48 minutes and 59 seconds west. That is a complete and accurate and unique location on the surface of the planet. If I left off the north and the west, it would not be complete, because I could be at 46 degrees 36 minutes and 39 seconds south as well, but I would be nowhere near Mattawa. I'd be in the southern hemisphere. But on some maps, you might actually see this labeled as negative 119 degrees, blah, 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 blah. But we're going to use positive numbers in this class. Okay, just a couple other things to talk about. This video is getting a little bit long. I was hoping to wrap this up sooner, but we're almost there. There's two other things you're really going to need for this first lab. The first, we need to talk a little bit about map scales. Anytime you've got a map, you need some other information to tell you how far things are apart from one another in the real world, on the ground, right? A map is a model of the real world, but unless we know how that model fits the real world, it's not very useful to us. I mean, I could take a world map and that tells me some information, but I could also make a map of my classroom, right? But the scale is going to be a lot different. There's two main types of map scales. There's what's called a bar scale, and almost every map, most like professionally made maps actually have both of these. But the bar scale is, they both have their strengths and weaknesses too. Bar scale is pretty cool. It says, okay, this distance right here, this bar, is 1 mile on the ground. So if I took that anywhere, I could measure a mile on the map. And then there's this ratio scale where it just says 1 to 10,000, or it might say 1 to 24,000, or 1 to 100,000. What the ratio scale does is it tells us that one of any measurement, centimeters, inches, thumbnail widths, doesn't matter. One of any measurement on the map is however many of that same measurement in real life. Right? So if I'm looking at a map and I throw my ruler down on there and I measure 1 inch from point A to point B, if that's a 1 to 10,000 scale map, that means it's 10,000 inches between point A and point B in real life, on the ground. If I were walking from point A to point B, I would walk 10,000 inches. Now they both got their strengths and weaknesses, right? The cool thing about the bar scale is if I go photocopy my map and I want it to say I've got a big map and I'm like, I want to fit this all on one 8.5 by 11 sheet of paper, and so I shrink it way down. That bar scale shrinks down with it, so the bar scale is always going to be true. The ratio scale is only accurate at the published dimensions of the map, if that makes sense. If I shrink the map, my 1 inch on my ruler hasn't changed size, but the map has, so it's no longer 1 to 10,000. So all the maps you're going to work with in this lab, they all have map scales. It's usually found either at the top of the map or the bottom of the map. I think they all got bar scales too. You're mostly going to use the ratio scales. The other thing that you will need to do for this lab is unit conversion. Oh, Mr. Dermond, geology rocks, right? What are we talking about math for? It's the language of science. Unit conversion, you guys have all probably seen this and done this before, maybe a bunch of times. Maybe this is so easy you don't even have to think about it. Maybe you're like, oh man, it's been 2 years, I don't even remember. So here's a quick crash course. You are going to multiply across by fractions that are equal to 1. What do I mean by that? I mean, you know that there are 12 inches in 1 foot. So if I made a fraction and I put 12 inches on top and 1 foot on the bottom, they're different numbers and they're different units, but the distance is the same. Is it not? 12 inches and 1 foot are exactly the same distance, so that fraction, in a sense, is just 1. And then here's the second part, is so you're going to make a series of these fractions, and you're going to just multiply straight across. And units that show up on both the top and the bottom of this stretched out equation go away. So here's your example. 1 mile equals how many inches? This is how I would set it up. Start right here with 1 mile. Put it over 1 because anything is just that thing over 1. And I could multiply that because by 5,280 feet in 1 mile. This fraction right here is, we're just multiplying by 1. But I've got miles on the top here, so I put miles on the bottom here because I want miles to go away, because remember, I'm trying to find out inches, right? So miles on top. So I'm going to build this fraction. I'm going to make sure to put miles on the bottom. And that will leave me with feet. Feet don't cancel because I don't have anything to cancel that with. But I want to get to inches, so I need another fraction. So I multiply it by 12 inches in 1 foot. Again, just 1. Same distance. Now I've got feet on top, feet on bottom. Those will cancel. And the only unit I'm left with are inches. And then I just multiply straight across. I go 1 times 5280 times 12 on the top of my fraction. 1 times 1 times 1 on the bottom of my fraction. I end up with 63,360 on top, and 1 on the bottom, which of course just equals 63,360. My units will cancel, miles will go away, feet will go away, and I'm left with inches. So I would plug in inches down here, and I would be left with 63,360 inches. All right, so here's what you got. You got your documents. There's the lab document. There's a copy of that for you. There are the PDF files of the maps. And this last little bit is crucial. Your Chromebooks don't really care for giant PDF files. It turns out that if you try to open those files out of Google Classroom, your Chromebook will complain. And if it does manage to get it open and you try to zoom in, it will be all blurry and ugly and you won't be able to make anything out, and you're going to call me and complain and say, Mr. Dermond, I can't make this work. Here's how you make this work. When you see those PDF files in Google Classroom, the thing you want to do is download them to your Chromebook. Download them to your files in your Chromebook. And rather than try to open them through Google Classroom, if you go to Files and then tell it to open it, oh, sorry, it's late, I'm almost done. If you go to your files and tell your files to open that PDF, you open it through Chrome, but open the file, it will open up in a new tab and it will be crisp and clean, and you can zoom in and in and in, and it will stay nice and crisp and clean, and it will be much easier for you to use. So again, download the maps to your device and open them that way. Do not try to open them through Google Classroom. It will not work for you very well. Okay, we're going on 26 minutes here. I need to be done so you can get started. Like I said, we're going to be working on this asynchronous lab over the course of the week, so you got plenty of time. As always, email me if you have questions. I'll be available for office hours during our asynchronous afternoon sessions, and I'm just so excited to get started. I'm so excited for this class and this school year. We'll see you guys on Zoom. I hope you all have, I'm trying to think of when you're going to see this. You're going to see this on Monday afternoon. I hope you have a great rest of your day, and we'll see you in the morning. Take care.